So moving into the last part of this lesson, we're focusing on one main thing here. It turns out that not every function has an inverse that is also a function. Okay, so we're going to focus on that idea. But let's introduce an example here to help us think about this that we've already kind of done together as an experiment in class. So this function here, x minus 10 all squared plus 7. Find the value of a such that f of a equals 11. Now don't get too confused here. I'm putting this in formal notation, but really what we're saying is, if we have a minus 10 squared plus 7, and then that results in 11, right? So what we're saying is we're given an output, and we want to know the input that made that output. What would you get? Okay, so if you solve this, it seems straightforward. Just backtrack it, right? Subtract 7, take the square root, and then add 10. Boom, we get 12. But is 12 the only number? There's a lot that we can think about that we've learned here. First of all, this is quadratic. And you and I both know that there's actually going to be two things, unless it's the vertex itself, which this is not. There's going to be two different possibilities. Well, here's where we get to the problem here. When we square rooted both sides of this, technically this has two possibilities. Plus or minus 2 both result in 4 when I square them. And so a could be 12, but it could also be negative 2 plus 10. So it could also be 8. This leads to a very important idea in functions. Okay, so more notation and facts to put in our list. So functions where just one input makes one output are called one-to-one. That makes sense. One input to one output. Now the function we just looked at in the last example, it's not one-to-one because we saw there's two inputs that could make one output. All right? And there's a fact now about inverse functions. Only one-to-one functions have an inverse function. But there is a way to deal with non-one-to-one functions. We can make them one-to-one. So we're going to illustrate with an example. So we're going to use the same function that wasn't one-to-one a moment ago, and we're asked to restrict the domain to make it one-to-one. And this means its inverse is a function. Okay, so being one-to-one also means that its inverse is a function. Let's dive into the graph actually and take a look at that.
So let's take a look at this. We all know that this is a parabola. We can see that it's in vertex form, so we know the vertex is at 10, 7. Problem is, it's not one-to-one. If you remember, we talked about the symmetry is what causes it to not be one-to-one. So any of these guys over here that have a match on the other side, it makes it so we could think of this as many-to-one, right? Because it has multiple inputs that all give the same output. And for it to be, for the inverse to be a function, we need to make that work. So watch, if we want to create the inverse graphically, an easy way to do it, remember we like it to be solved for y. But we did talk about how just switching the role of x and y is inverting. So notice here, what I typed in was exactly just literally switching x and y, and it will actually put what the inverse is there. Now, a special note here, there is some symmetry. In fact, whether or not you noticed it, y equals x is the line that it's symmetric across. So we've been used to seeing symmetry that's like reflected across just the y-axis or the x-axis or something. And this is a new type of symmetry likely for us graphically. But this is another fact that we'll write down later. If you have two inverses, they're always reflected across the line y equals x. Now let's get to answering the question that we set out to answer. How can we restrict the domain of the original one so that the inverse is a function, right? Right now the inverse is not a function. There's multiple outputs for the inputs. Remember, that's what a function means? Like for example, 10 here has 2 outputs. In fact, all these outputs have 2, except the vertex, of course. So what could we do to the red one so that the result, when I did the reflection, is a function? It doesn't have that double up. Oh, just cut it in half, right? And this vertex turns out to be an important point. Let me share with you how we're going to do this. In Desmos, you can type curly brackets, and I'm going to do x greater than or equal to 10, and it only keeps half of it. Now, we could have kept the left half, but it's just standard to keep the right half. And what's that effect going to be? Well, for the inverse, I type y greater than or equal to 10. And we can see that now there's still the reflection across the line y equals x. But the purple one is now a function, right? So we've actually forced the parabola to be one-to-one so that its inverse is a function. And this is how graphs work with inverse functions.
So you've seen if we take a graph and reflect it across the line y equals x, you get the inverse. But functions like parabolas, when you invert them, the result is not a function, and it's because they weren't one-to-one. So we have to restrict the domain. So the domain restriction in our case would be x greater than or equal to 10. Now for the last fact for today, the graphs of a function and its inverse are reflections across the line y equals x. And again, that should make sense because remember we said y and x swap roles with each other, the domain and range. So it makes sense to reflect across the line y equals x would be what happens. Alright, the actual very last thing for this lesson. So here's a function, also quadratic, so we know it's not naturally one-to-one, right? So we're thinking natural and restricted domain again. Restrict its domain to make it one-to-one. Remember the key place here, location, is going to be any turning points, right? So it's vertex. So restrict the domain, find the inverse function, think about what we did prior, right, with reversing the steps, and then sketch the graph of both of those things like we just did. So go ahead and pause now and do this yourself. Let's see how you did. So again, the x-coordinate for the vertex is -3, right? So we just need to keep the right part of that. So x greater than or equal to -3. Well, finding f inverse, remember we need to not only undo each operation, but we need to go in reverse, right? So I need to add 8 first, and then square root to undo the squaring. And remember, we don't need to worry about the plus and minus, because what that did was that kept the top half of the sideways parabola and the bottom half, but we're only keeping the top half. So there's the inverse function, and then of course -3 at the end. And then graph the restricted function, and then also the inverse. So this function has its vertex at -3, 8, but we don't want to keep the whole thing, right? Only the right side. And because this vertex is at -3, 8, if we swap those, right, 8, -3 must be where the other one is, and it's just going upwards. And I put in this line y equals x to help us remember that this has been reflected like that. Okay? So that's it for this lesson. Again, happy math, and we'll see you next lesson.